Numerical integration is desired for working with finite elements. The integrals involved in the stiffness matrix and the equivalent nodal load vector are too complicated to do by conventional integration. The standard integral that we use is the Riemann integral, and here we're going to replace it with sampled points on a function multiplied by weights. We'll give the background of the Gauss integration and show its use extensively in one dimension. We'll talk about Radau and Lobato integration, show how you can extend to non-symmetric domains. We'll talk a little about two dimensions and finite element applications, which is the real use of the method here. And we'll have some problems to illustrate these different cases. We'll start out by looking at integration of a real variable on a one-dimensional domain. So it's going to be a function of x. Generally speaking, you would have this function f shown as a dashed red line extending through your region of interest. I'm showing it dashed because I don't really know that function explicitly. I can sample it, though, at specific points on this axis. The goal is to find the shaded area under the curve. And of course, as we mentioned in the lecture on interpolation, the difficult part of finding that area is to characterize the function, because the three straight sides of this figure are not difficult to find. It's only bounding it at the top. So what we're going to do is replace the conventional Riemann integral on the left here with this finite sum on the right. And that sum has only n terms rather than infinity. It has weights that will emphasize our different samples, and then the value of the function that is being sampled at these coordinates x sub I. Sometimes these sample points are called abscissa, and I'll use the word sample point and abscissa interchangeably. One author, Hamming, says that numerical integration follows in 4 different paths. The first type would be integrating a function by sampling at fixed points. And there are 2 emphases here. One is that you are only evaluating the function, and that these fixed points are predetermined perhaps by making the points evenly spaced. A second method gets something like a primitive derivative through differencing. A third approach would actually calculate derivatives as well as the functions. Now, evaluating the derivative is going to even be more expensive, but there are methods that need that. And lastly, our methods, and Gauss integration is characteristic of this, that require samples of the function at specially chosen sample points. Now, these are not equally spaced. In fact, these are optimally chosen to reduce error. Let's look at a concrete example of numerical integration. It's a simple method called the trapezoidal rule. Here, we're looking at samples of the function at evenly spaced points on the axis, and then one imagines that the area under the curve is subdivided into small trapezoidal regions connected with straight line segments from the intercepts at the top. Then it's relatively easy to sum the total area under the curve using the trapezoidal formula, which says that you use basically the average height times the base of each little trapezoid. An interesting thing is that the left sample point contributes only to the first calculation, but the interior sample points calculate both to the area on their left and their right, and as such are doubly counted. As a result, when you sum up these various trapezoids, you find that the end points have weights that are, in this case, the delta x over 2, have the weights delta x times the samples, and then finally another exterior point. This formula is robust in that it's hard to fool it very much, and I know that rather than using an intricate formula, there are times when you would like to use such a simple rule. And I did that myself once in my master's thesis years ago when I was integrating strain energy in a delta wing to get natural frequencies. And I found that a very intricate rule called Multop's quadrature that really was complicated. It used fitted sines and cosines and got weight functions, that is, weight constants that were large numbers, both positive and negative. So I don't want to make fun of this simple trapezoidal rule. It is the most robust of all the methods, the least likely to go wrong. A second integration rule is Simpsons rule, and this fits small sections of parabolas through the curve. Here you have to have an odd number of evenly spaced points, and you can subdivide your area into regions that have 3 sample points, and then you can pass through these intercepts at the top, you can pass a parabola. Likewise, with this next area, you can pass another parabola. And without working out the details, the weights come out in a different pattern. The end sample values are not weighted highly at all compared with the middle sample values, and the ratio is 1 to 4. Now, because the end value occurs not only in its own area, but this point will also affect the next one, you then, when you add these up, get the weights going in the ratio 1, 4, 2, 4, 2, 4, 2, 4, 1, because the those end sample points are used twice. Now this formula is a little more complicated, a little less robust, but still is useful in many cases. Now let's look at Gauss integration. This is a very efficient method. The sample points are chosen for accuracy, and when that's done, you get essentially twice as much value from each sample point. So it's a little like magic, but it's a logical approach where you say, where can I put these sample points to give me the most accuracy? And the answers are sometimes surprising. They're often irrational numbers, so they're not necessarily evenly spaced or nicely spread across the domain. Now, for practical purposes, rather than looking at a general definite integral running from A to B on the x-axis shown here, let's instead look at a symmetric domain extending from -1 to 1. Then the function will be defined as this dashed line over that region. We'll use a variable xi as our integration variable. Later we'll learn how to do the calculation on the unsymmetric domain, which is the more physical problem. But the reason we want to do this is that it's easier to calculate the weight constants when you do it on a symmetric domain, because you have a symmetry in the problem. Let's develop the Gauss integration by considering the simplest domain that we can, namely a one-dimensional space. So we're basically asking for the area under a curve. Here we're going to convert our problem from thinking about a general function, f of xi, on the symmetric domain, into a problem where we have a series of terms that are polynomials. Now this is a legitimate Taylor expansion, so there is some basis for doing this. It makes us think then, rather than some fuzzy question about accuracy of a general function, into a more specific set of questions. How can I best evaluate the integration of a constant, of a linear term xi, of a quadratic term xi. And you'll notice that the expansion in the Taylor series involves these coefficients, but they play a rather placid role outside the integral. And so if we can resolve how to integrate these polynomial terms successively, then we'll know how to calculate a general function. The usual approach here, and it's logical, would be to require that you integrate successfully the longer wavelength terms first, much as you would in a Fourier analysis. So we would demand, first of all, that you can integrate a constant, then secondly, that you can integrate the quantity xi, then xi squared, and on up in the polynomial series. When I first wrote down the replacement of an integral of the Riemann type with a sum of sample points and weights, you might have noticed that each sample point generates two unknown constants in that process. One is the weight to be ascribed to the sample, and the other is the location of the sample point. And so if you have n sample points in a Gauss integration, you're going to have 2n constants to be evaluated. Now, I repeat that here by saying n sample points are going to generate 2n unknowns. You'll get n weights and you'll get n abscissa. Now, the way that we're going to evaluate those constants is by creating what are called defining equations, and these are the conditions that the integration process be exact for the various terms in the expansion, so for various polynomial terms. And if we have n sample points, we're going to have 2n unknowns, and we're going to need 2n defining equations to get the job done. Now, I think this bookkeeping I've just done is a little bit unmotivated, so you'll see it from the examples that follow. The simplest example we can start with, and now we're really going to generate a replacement approach here. It's a replacement sum that is going to be used instead of this conventional integral. So we'll have to find a weight, w, and a point at which to evaluate the function xi1. There are two unknowns here, and then we're going to require two defining equations to evaluate. We now set up two defining equations based on accuracy need, and that will give us two equations to find these two parameters that we seek. The first defining equation physically is just that we ask that we can integrate the area under this curve here. And it's on the symmetric domain from -1 to 1. Mathematically, it's expressed by this law that we must be able to integrate unity from -1 to 1 and get an exact answer. What is the exact answer? The exact answer is 2, because it's a 2-unit area here. The way I'll do this is basically work on both sides of the equation and come down from above and put in what we know about this sampled function. Now, it turns out no matter where you sample on this axis, you're going to get a unit value as your intercept up here. And so therefore, I'm okay to put a unit value there, and that immediately gives you that W1, the sample point, is the number 2. The second defining equation is a statement that we must evaluate xi exactly. And over here I show the picture. This time it might seem to be a trick in a sense that the total area is 0, which I show on the left. But that's a useful concept. Now, no matter where you sample, at some sample point xi1, you will go up and you'll intercept the curve, and then move to the sample point here, which is f at C1, and that will in every case turn out to be the number C1 itself, because it's a 45-degree line. And so we have our second equation. Since we already know W1, we can see that C1 should be 0. And so putting that back into our original representation of this integral, we find a weight of 2 and a sample point of 0. Well, we have our first Gauss integrating formula in our hand, and now we have to find something to do with it. So let's look at some examples. Here's our integrating formula. It would be called a one-point integrating formula, and we could use it perhaps to integrate some function, such as this straight line function here, 3 plus xc. I'll show it as a solid line here because we know what it is, but nevertheless we're going to evaluate it by sampling. Now, it really seems like a little much to say that if you multiply by 2 a sample value at the origin, that you're going to get an exact answer. But we know that from our defining equations we can exactly integrate a constant and then a linear function. So we're going to get an exact answer if we take a sample at this location of c equals 0, find the intercept, and on that function the intercept will be the number 3. So I'll put in here 2 times 3 is 6, and that will turn out to be exact. We can check that by doing the conventional Riemann integral and finding that indeed that is the area. Or you can use your common sense and see that that number sampled at the value of c equals 0, or an abscissa of 0, is actually is the same as this enclosed rectangular area, which is 2 units wide and 3 units high, and so we know that rectangular area is going to have 6 units. And then you can see that on the plus minus side the actual function will contribute equal positive and minus terms over and above that particular rectangle. So either logically or doing the integral in the conventional way, you can prove that this is exact. The previous example was an easy one because the function that we were integrating was a linear function, and the integrating formula could be used exactly. Let's now consider that one-point formula applied to a higher degree polynomial, such as this red curve shown here. When you use the integrating formula we've developed so far with only one sample point, you are asked to sample at the origin here. You find this intercept, and effectively what was done was to block out this area shown in the rectangle here. And you can see that that area will underestimate the true area of the more complicated function. So sadly in this case our one-point formula underestimates the answer. So this can happen and often is acceptable because you would rather do a cheaper integration and have some error involved in it than to carry enough sample points to do an exact solution. Now we can make some conclusions in one dimension. When you have n sample points, you know that requires 2n defining equations. And if you satisfy 2n defining equations, you're satisfying sequentially the polynomial terms 1, xc, xc squared, and so on, up to 2n minus 1 in polynomial degree, where the minus 1 comes about from the need to integrate the constant term. So you can actually tell how many sample points you need when you're integrating in one dimension. On the other hand, if you have transcendental functions or higher degree polynomials, then your answer will be only approximate, but that's quite often acceptable. You might also have experimental data which typically, for instance, in some problems could be Bessel functions or Airy functions, some other actually infinite series in polynomial terms, and again, that would just be an approximate answer. Let's now look at a two-point Gauss integration. This will require 2 sample points and 4 defining equations. So we replace this Riemann integral with these 2 terms. The defining equations include the previous 2 in philosophy, namely that you have to integrate this rectangular area under the unit value. And as we found before, that was 2 units. Now we have 2 quantities to evaluate here. Since the sample will give you a unit value no matter where you sample on the axis, you get units there, and you get this first defining equation. The second defining equation, again, has to do with areas under the linear curve, which is 0 because of cancellation. And when you sample at point C1, the functional value becomes C1. When you sample at C2, the functional value becomes C2, which I show here and here. So our second defining equation is this one. And notice that the variables are coupled together. The third defining equation has to do with integrating a parabolic function. Here we show the parabola on the symmetric domain. We can do the Riemann integral directly and find that it's an area of 2/3. When we evaluate the function xc squared at the points c1 and c2, we get these 2 values of c1 squared and c2 squared and get this new defining equation. Again, rather seriously coupled. Lastly, the fourth defining equation is an integral over a cubic polynomial. Again, you get by cancellation a 0 integral exactly, but the approximate value is shown on the right. So we really have 4 nonlinear equations in 4 unknowns. This is a relatively tough problem to solve as it stands, and I'm going to take a shortcut, which is a fair one and which is correct. Namely, that if we're to choose 2 sample points on this domain, is it likely that they would be bunched up on one side? No, they'd probably have to have one on one side and one on the other. Is it likely that they might even be symmetrically disposed? And the answer is yes, because you have no idea where that a true function that you're integrating, a general function, would fly through this space. It might go this way, or it might be the mirror image the other way. Therefore, it is correct to assume symmetry that the 2 sample points are equally spaced about the origin. Now, that relation can be used to eliminate one of the 4 defining equations. Because of that simple symmetry equation, we now can ignore the 4th of the defining equations. It's pretty complicated because it has cubics. We go into equation 1 and solve for the one weight in terms of the other weight. And that plus the symmetry condition we'll put into our equation 2. So this was the location where W2 would have occurred. And then this is the location where C2 would have occurred. So we're using all the information at our hands now. And when we do that, we end up with an equation 2C1 times the sum W1 minus 1. Now, there are 2 potential solutions here. One would be that we take C1 equal to 0. But that wouldn't be useful because then C2 would also be 0, and we would have 2 solutions or 2 sample points bunched at the origin. So no way are we going to sample the function twice in the same spot. We know that that's not the optimum way. So clearly the other solution is the proper one, which gives a unit value for the weight. And then using the equation above, we find the other weight has to have the same value. We didn't prescribe this, but this symmetry was obtained as a result of our process. Now the third equation then can be solved for the sample point because it was C1 squared times W1 and then W2, which is also unity, times minus C1 squared. And adding that together, there are two of those, so it equals 2C1 squared. Then the 2's cancel, and you get C1 squared equals 1/3. Or, as shown here, C1 is the square root of 1/3, which is an irrational number. Now, naturally, you wouldn't try to locate that point with such terrible precision. I've just carried enough numbers to impress the viewer, I guess. C2 is a negative of that, just to show that they really are spaced symmetrically about the origin. Our integrating formula for a two-point integration now becomes the integral of this general function on a symmetric domain is unity, which was the weight, times a function evaluated at plus 0.577, and then a weight of unity times a function evaluated at minus 0.577. And since we were able to satisfy 4 defining equations, that means this integrating formula is exact for a cubic, 2n minus 1. Okay, well, we need to nail this down with a numerical example, so I'm going to pick kind of an exotic example here and see if we can exactly integrate it. Suppose I do take a cubic, which our new formula should exactly integrate. What I want to do is evaluate this expression numerically. This is a pretty tough function because it's a cubic. It has 3 zero crossings, which is the maximum that a cubic could have in that region between minus 1 and 1. I show it here with a heavy blue curve, and we're trying to find the area under it, which is a positive area in the red cross-hatched regions and a negative area in the green cross-hatched regions. So knowing how to Gauss integrate, you could take this curve into your neighborhood bar and say, I can integrate better than anybody in the bar, and then take bets and so on. Well, I think the people would be astounded if they learned that you could take a sample point at plus 0.577 and all those decimals and come up here and take this one spot, and then you evaluate at minus 0.77, etc., and find this spot. And if you told them all I have to do is add this number on the left and this number on the right, and I'll get the exact area under that curve. Well, naturally they wouldn't believe you, because who'd believe an engineer in a bar anyway that's doing too much bragging? We don't have that curve available, so we'll have to evaluate those two functions numerically as shown here. So here's our original desire to find this integral. And then we do evaluate at the right sample point here and at the left sample point here by putting the sample point value, in other words the abscissa, into the polynomial locations. Carry that out and you get 0.16666 and so on to as many figures as you'd like. The analytical answer can be done in the conventional way and evaluating the quartic function at the left and right ends, and you get 1/6. So you really have an exact answer to that problem. Now, there isn't any error in the algorithm involved here, but there could be round-off error, and I'd like to distinguish those two. Sometimes, and I've seen in textbooks where people have illustrated Gauss integration and have not pointed out the distinction, because they've done sample problems that should have been exact, and they get error in something like the third or fourth significant figure, and it leaves the viewer thinking maybe it's approximate. So Gauss integration is either exact or it isn't for a given function that you're integrating. There are two modifications to Gauss integration that can be easily done. The first one would be to fix one of the sample points a priori at one end of the symmetric domain. The reason you might do this is that there might be some physical application where you already know something about that end, or there are some cases where that end is special. For instance, there is a case in the literature of a triangle in which there are lines upon which this integration is done, and they intersect at the left vertex, and so that point was chosen a priori. What that does is basically rob you of one of your defining equations, because the location of that sample point is not left to be part of the solution. In other words, it's not optimum. Lobato is a similar idea, except that you would use both endpoints and thereby eliminating two defining equations. So there's a little loss of accuracy here, but perhaps some convenience in special applications. The work that we've done so far has been for the symmetric domain for ease of computation. But now let's try to connect back to the real world. Our original integral really was this integral on the domain AB, shown in this figure, and what we've done basically is convert that over to the symmetric domain. Now, how is that really done? Well, it's basically the change of variables in an integral. So there is a linear mapping, it turns out, that would let you go back and forth between the x and the c variables. That relation has a constant shift, which effectively shifts the center of the physical domain, and then it has a stretch or shrink factor to account for whether the physical domain is bigger or smaller than 2. And what our goal should be really is to convert one integral into the other and see how that works. So we'll take the physical integral here and turn it into a variable or an integral on the dc variable. To do that, you need to evaluate the integrand at the c location. That doesn't require anything particularly special other than the notation. But you've got to change the limits, and you've got to change the integrating variable. Now, the integrating variable is changed by taking dx equals 2, and then you merely do the differential form of the equation above to get that it's this stretching ratio times dc. This actually is sometimes called a Jacobian. It's a stretch ratio when you're going from one integral to the other. And then that will show up here where dx used to be. Then the upper limit that would be x equals b would be for c plus 1. You can show that by putting b into this formula and then calculating c. You might want to pause and do that just to prove it. And likewise, the lower limit goes with c minus 1. So all told, we've now converted from the real domain over to this symmetric domain. So we will factor out the stretch constant from the integral, bringing it in front here. Interestingly then, this integral now becomes the symmetric form that we work so much with, and we'll replace it with our series of weights times sampled functions. Now, up to this point, we've sort of been talking about going from the physical world to the symmetric artificial world, but at the last step, as we see here, we can actually interpret this in the physical plane just by realizing that the c can be mapped into the x, and if you allow me to call those the x sub I, which are the sample points in the real world, this formula now has been converted to one that can be used directly on the non-symmetric domain. Finding these x sub I is not hard because you use that linear mapping that we started with. And indeed, all these formulas let you go back and forth between the two domains because they're linearly related. Now let's move from one-dimensional discussions of Gauss integration over to two dimensions. Here, if we have an integral in 2 dimensions, we like to replace it with a similar series that we used before. It would be a finite series with n sample points. There would be weights times functions that are sampled at certain abscissa. But the location of the sample point this time has 2 coordinates. There would be, for such a sample point, both a xi sub I and an eta sub I measured from the origin. Each such term in this series then would have 3 coefficients to be discovered and would require 3 defining equations. Okay, so you can add up the number of sample points required to give certain accuracy in general polynomials. Now let's take an example of the continued polynomial expansion below here, that 3 terms would be sufficient to have a complete linear polynomial, and that would take only 1 sample point. If you had a complete quadratic polynomial, you have to come out to, let's see, to d c squared, this one here. It would have 6 terms, and that would take 2 sample points. If you go to a complete cubic, out to this point, you're going to have 6 plus 4 is 10, and for that you're going to need 4 sample points. So this continues on, and I've summarized that in the next figure. In fact, I carry out this logic all the way to a quintic, where you have to have 7 abscissa. But you know, this really isn't done in practice by using consistent Gauss integration for the dimension involved. Instead, people actually use one-dimensional ideas repetitively. And in some ways that's a disappointment, but it shows how tough a problem it is. I think maybe in the future people will be developing true 3-dimensional Gauss integration more. What we're talking about is roughly along this idea, and this was illustrated by Zienkiewicz in his book, that if you have a function, and I'll take a specific function just to tie this down, that when you integrate in one direction, say across the xi, so you're taking a cut through here, then what you're doing is replacing the first integral, the xi integral, with this series of terms, and which requires evaluating the xi sub I at specific points. Then, viewing that as an integrand for the second integration in the vertical direction, you're required to make the same kind of cuts on the j variable, so you have weights j and eta j terms. By factoring these out together, the weights out together, you get a combined weight times a function that's evaluated alternately at the ith points and the jth points and so on that are needed here. And these are the kind of ideas that are used in practice. This seemed like real magic to me, but I started following it in regard to certain simple functions, and it seems to have logic. But it's a complicated idea. I think that the development of Gauss integration in 2 and 3 dimensions has become more of a mathematician's area than an engineer. So I think we can relax and conclude that the codes are doing these ideas in correct ways. We need to tie down our theory a little bit and show where it's used in finite element applications. I stated this earlier, that our 2 big reasons for interest in Gauss integration are integrating the strain energy density that leads to the stiffness matrix, and then secondly, finding the equivalent nodal loads. Both of these would be very difficult analytically, especially on the more complicated elements. And so you'll find most of the advanced elements now are being numerically integrated, and most of those are done by Gauss integration. I'll sketch a few typical elements that have been numerically integrated. Here's a four-noded rectangle with, as you would expect, a rectangular pattern of Gauss sample points. Here's a quadrilateral where the pattern now would have to be skewed to reflect their mapping from the C-eta coordinate system. That's not shown here, but would probably extend something like this. We know that we can go back and forth between those coordinates. Merv Olsen, who was a Caltech classmate of mine years ago, did a clever triangular element in bending. He used one sample point at the left vertex, which was fixed a priori, and then allowed the other two Gauss points to slide along these dashed lines to find their optimum location. Lastly, here's a solid element with a 2 by 2 by 2 pattern shown. Irons figured out this numerical scheme some years ago. The MSc Nastran version is called the hexa, and it actually uses a 3 by 3 by 3 pattern for the direct strains and a 2 by 2 by 2 pattern for the shear strains. And so you can see that people are starting to tinker with the Gauss points and how many to use. Also, some of the codes, particularly the nonlinear ones, will allow the user to choose how many Gauss points are needed through a given thickness. The first problem in our problem session will be an unsymmetric Gauss integration. We want to find the integrand, which is a quartic, integrated in the region from 2 to 10. We would be happy to have an approximate value of this integral, so we're specifying a 2-point Gauss integration. Does that in fact, however, give you an exact answer? So we're expected to do the integration and then comment on the accuracy. Our solution will not be exact, and the reason is that the function that we're going to evaluate is a quartic. That means it has 5 terms in its polynomial involving 5 coefficients. 2 sample points will only give 4 defining equations, so we fall short 1 polynomial degree. We could integrate a cubic exactly, but not a quartic. The unsymmetric formula here for this integration involves the stretching ratio, the weights, and then the function evaluated this time at the physical coordinates x1 and x2 that correspond to the one-dimensional Gauss points. The linear mapping involved has this shift. Now we'll look at our first Gauss point. It'll involve this shift, this stretch, and then we'll have to insert the first Gauss point in the C variables, which we do here, and we come up with the first physical integrating point located on the axis below. The second integrating point is found likewise. We had a negative Gauss point, and when you put that in, you find this location. So you can see that those are symmetrically displayed in between the interval 2 to 10. We can complete our solution now because we can evaluate that function at the sample points. We know the function analytically. We put in the value of the Gauss points to get the sample at x1, put in the Gauss point to get the sample at x2, and we get these two rather large numbers. When we add the stretching involved, we find that there's a weight of 4, and we end up with this minus 56,000 number. The analytical solution, on the other hand, is given below here. and done in the conventional way, ending up with a fifth degree polynomial evaluated at the endpoints, and there you get a similar number, large negative number in the 57,000 range. And our Gauss integration was within 1%, but it's slightly low. Now that would be useful then for many purposes. Problem 2 requires the viewer to develop a special purpose Gauss integration formula. This is a little contrived because we're trying to think of an integration procedure where you have a formula that is a quintic polynomial at most, but has no linear or constant terms. And since you'll be doing this same type of polynomial over and over, it's proposed that it's worth your while to develop a special formula that doesn't need to integrate constants and linear terms. You need to develop the defining equations and then solve for the abscissa and weights. Well, the solution first would involve determining how many sample points are needed, and since there are 4 terms in this family of polynomials, you're going to need 4 defining equations. That will require 2 sample points because each one gives 2 defining equations. The new Gauss integration formula is shown here, where the weights W1 and W2 are not the conventional ones, and neither are the sample points. Probably. We couldn't say. They may still be spaced somewhat close to the optimal one-dimensional case, but we don't know that yet. Okay, so we're going to start out with our first defining equation for a quadratic. This is the first polynomial term that can enter. And as we've seen before, and working on the 2 sides of the equation, the exact integral under the parabolic curve is 2/3, and then we evaluate the function picking up the c1 squared and the c2 squared. The cubic polynomial likewise is integrated, and the exact value is 0, and then we end up with the cubic terms. We continue on with the quartic and the quintic equations. I'll just write these down without drawing fancy pictures, and the quintic again is an odd function with a 0 value. So this gives us 4 equations in 4 unknowns. If we make the symmetry assumption, and this time I'm going to be pretty bold in order to crash through this quickly, I'm going to assume that on this symmetric domain, both the sample points are symmetric about the origin and the weights. We assumed the first and found the second as a consequence in an earlier solution for the classical formula, and now we're assuming both of those symmetry ideas. We'll use those symmetry assumptions now to simplify the 2 equations that we need. Equation 1 involves both weights and both abscissa, but we set W2 equal to W1 in this location, and then we set C2 equal to minus C1, and then when it's squared it comes out positive. The right hand side can be summed to give this expression, and then gathered over here at the right. It turns out we need to use equation 3, which was the quartic equation, and when we do the same process and then gather these terms, we end up with 2W1 C1 to the 4th gathered over here. Now these are 2 nonlinear equations in 2 unknowns, and in general there could be many solutions or no solutions. Nonlinear equations can be pretty difficult. We need solutions for the abscissa that lie within our range from -1 to 1, and that would certainly be one condition that we would put on. It turns out you can solve by dividing equation 3' by equation 1', and that will eliminate the weight, you see, and give you an expression only for C1. C1 then pops out directly and comes out to be this particular square root. C2 would be the negative of that. Now, knowing those numbers, you can go directly back into either equation and find the weights. And so we use equation 1 prime for the first weight, and then the second weight has been set equal by symmetry. So we do end up with an integrating formula. This is an exact formula for that class of functions that we wanted to attack. Problem 3 is more of a rote exercise where I'm expecting people to turn the crank and grind out a Gauss integration. We've been given a polynomial here which has 6th degree terms. We're asked to do the symmetric integral over the region -1 to 1 using Gauss integration and 3 sample points. And then we're asked to comment on whether this is exact or not and why. Now, this is going to require looking up the weights and abscissa from a table, and I have some in my course notes, and any textbook on finite elements would have such a table. The formula that's used is this one with these weights, these 3 weights, and then these 3 abscissa, including the one at the origin. And notice the symmetry again. We have a point at the origin, and then we have plus and minus numbers symmetrically disposed about the origin. Now, will this give an exact integration of a 6th degree polynomial, which in general could have 7 constants in it? And the answer would be no, not a conventional Gauss integration, because it would have had 6 defining equations and would have been optimized to integrate the constant, linear, and so on up through the x to the 5th terms. So you would need a 4-point integration to get an exact answer. The evaluation of the function at those 3 sample points is the biggest part of the labor here, and we'll just skim through that quickly. Here we actually take the known polynomial terms and put in the first sample point and evaluate it. We then take the second sample point at 0 and evaluate, and that number is an easy one. And then we do the third sample point. We put those 3 contributions into their respective locations here and sum it up and get this answer. If you do the analytical answer, it's slightly higher, so we've underestimated a bit here. 12.96 versus the exact answer 13.14, but pretty good. Problem 4 has to do with Gauss integration of a beam element, and I'm going to try to tie our theory a bit more closely to finite element theory now. Suppose that you wanted to use Gauss integration to integrate along the length of the beam, that's the x direction, in a 2-noded Euler-Bernoulli beam. Now that's the standard Euler-Bernoulli beam that we've studied earlier. How many Gauss points are needed for an exact solution for the stiffness? How many Gauss points would be needed for an exact equivalent nodal load set up to parabolic load distributions? Really interesting questions. Now, you can see in the solution that the key is going to be that the beam shape functions are cubics. So we'll exploit this cubic nature of the shape function a lot. First of all, the shape functions enter into the stiffness integral in this manner with 2 derivatives. Now, since nx itself is cubic, 2 derivatives would be linear, so the integrand here would be a quadratic function of x. Therefore, there will be 3 constants involved in that polynomial, and that will require 2 sample points to define. to get an exact answer. Likewise, if we do the equivalent nodal loads and we have a cubic function here, and if the distributed loads are as much as quadratic, then you've got degree polynomials 3 here, 2 here. That means the integrand in total is quintic. In other words, 5th degree polynomial. Now that will have 6 constants involved and will require 6 defining equations, and that's supplied by 3 Gauss points. So interestingly, the stronger criterion is the one for finding equivalent nodal loads exactly. In problem 5, we're asked to develop a Lobato integration scheme. Given that there's a series of cubic functions to be integrated on the symmetric domain from -1 to 1, we're asked to use Lobato integration and find the abscissa and weights from first principles. And when we get done, we'll compare with Simpsons rule. At the outset, it doesn't seem there should be any connection because it's a completely different classical method. Okay, let's solve this. The cubic has 4 constants, therefore we know we need 4 defining equations. And here I've written down a general cubic showing those 4 constants. Now, the function is shown above, and in the Lobato method, you a priori say that you're going to sample at the 2 endpoints. So that, in effect, uses up 2 defining equations we might have had. So our 2 sample points only yield 2 defining equations. So clearly we need a 3rd sample point. We can do that by taking a point somewhere in the interior, which we'll call C2. I'll write down our new Lobato integration formula here. It has this series of 3 terms involving the red quantities that are unknown at present. We have the 3 unknown weights and then the 1 unknown abscissa. The defining equations are done in the same way as before, except that we know the location of the sample points at the 2 ends. We have to again integrate the constant, the linear, quadratic, and cubic terms, and we put in the values that are exact for those integrals. Then for the evaluation, we enter the sample point evaluation here in the middle term, and then we have the location of the sample points at the left and right end, and so we're able to enter those in those corresponding spots, and that gives us 4 equations and 4 unknowns. To solve those 4 equations and 4 unknowns, we'll take some treachery and cunning. One way is to recognize that symmetry again would require that the center sample point be at the origin. That knocks out the highest degree equation, namely the cubic one, and then we can write out the other equations, and those come in rather nicely when we put in the 0 for the central sample point. And if you take the second and third equations and add them directly, you get W3 is a 3rd. That's a 3rd weight. But then the second equation proves the symmetry of the weights. The first equation then will give us the remaining weight at 4/3. This leads to an integrating formula here, and as we look at that, we see it's a 1/3 of the function at -1, 4/3 at the center, and 1/3 at the other end, and that's exactly the same as Simpsons rule. So in this case, the even spacing didn't seem to give us much additional accuracy over conventional methods.